Welcome back to LIS570. This week we're going to talk about quantitative data analysis. We're going to build on the descriptions that we had of independent and dependent variables last week when we talked about quantitative data collection. And we're going to start to really put to work the assumptions that we have about working from, say, a positivist standpoint and using deductive logic. So let's jump in. So our agenda this week is going to look like this. I'll first talk about and describe some of what we mean when we say that we're using a deductive logic and we're using or applying statistical analyses. Then I'm going to dive into two broadly used statistical approaches within library and information science. That is the descriptive statistical paradigm and the inferential statistical paradigm. Okay, so all along we've kind of described this move or this interpretive step in our paradigms, that is in the commitments that we have to ontologies and epistemologies, as being about the justification for beliefs that we hold. Now, when we're working on qualitative data analysis, that what we talked about in a couple of weeks ago, is we're moving from, say, a set of specific concrete examples that we've observed, and we're interpreting those examples. We're putting them into a narrative and into a framework which helps us organize reality, which helps us make sense of, and which helps us explain why it is we think maybe certain things have happened the way that they have. Now, quantitative analysis is going to work from the deductive logic happening at exactly the opposite way, right? It's going to attempt to move from the general to the specific. And in doing so, it's going to take maybe theories that were developed by qualitative researchers, or maybe hunches and theories that we have that explain the world to ourselves. And we're going to design tests, experiments, surveys, specific uses of data that already exist in the real world, and we're going to try to see whether or not those align with the assumptions that we hold. That is, whether or not our theories have any weight. And we'll do that by taking specific measurements and looking for patterns or distributions in those measurements. Okay, so now the good news is around deductive logic and around quantitative analysis in particular is that up front, we do a lot of design work. That is, we have to specify what our hypotheses are. We have to specify what kind of data we're going to get and what particular attributes or variables within that data set we're going to analyze and how. But now the bad news is exactly what the good news was, is that it's really hard to specifically say what exactly we'll measure and what exactly we think about those measures in concrete ways that will allow us to come up with some very specific answers to the general theories that we have. So let's maybe look a little bit closer about what we mean by this kind of idea of good news and bad news in quantitative deductive analysis. All right, so I'm a bad news first kind of guy. So what is difficult about designing deductive quantitative analysis is that up front, we have to know exactly what our data will contain, and we have to know which measures we're going to put in which statistical tests in order to come up with valid conclusions about the hypotheses that we hold. That is, if we have up front a theory about the way that the world works, what we're going to have to do is put lots and lots of work into our design of a protocol to collect and to interpret our data through patterned measurements. So in a really simple example, let's think about a hypothesis that we might have about, well, something like dog food. All right, so does the shape of dog food impact the way in which dogs, maybe the volume of food that dogs eat, right? So our hypothesis is probably that it doesn't. We could say shape the food like fish, or we could shape the food like cats. It doesn't matter what shape it or form that the food takes, our dogs will eat it all the same, right? So we could test that hypothesis by doing things like measuring the amount of food that's eaten, measuring based on shape, measuring based on breed of dog, measuring based on time of day, right? There are innumerable factors that we could, say, record and try to understand their impact on whether or not a dog was, say, eating based on the shape of the food or not. Now, what we're trying to do in collecting all of that data, which may seem kind of extraneous to the thing that we're trying to understand, that is shape of food and volume eaten, is that we're trying to make sure that there's no biases creeping in, right? There's no external confounding factors. So what we're essentially trying to do when we work deductively or from a positivist paradigm is remove bias from our study. And one of the ways that we do this is by trying to record things like breed or time of day, because these are going to be factors that, when held consistent, they will allow us to show that it doesn't matter by breed, it doesn't matter by time of day. What matters is that the shape of the food, say, remains consistent based on how much the dog will or will not eat. Okay, so now the good news is that once we do that, right, once we come up with the specific things that we should measure and how we'll measure them, it's really quite simple to then go about executing our data collection and then our measurement of the data that we ultimately generate. So let's take a look at how we might test or how we might come up with some analyses from, say, simple data that we've collected once we've decided and determined upfront the design that we should take. So I talked about at the beginning that we were going to look at descriptive statistics and then inferential statistics. So let's talk about descriptive statistics first, and then we'll jump into what we mean and what we think about when we infer something through a statistical paradigm. So descriptive statistics help us do just that. They help us describe our sample or our population. And what is being described within that sample or that population are patterns from the observations that we've made about our sample or our population. Now, it's important to note that descriptive statistics don't necessarily allow us to make firm conclusions. They rarely help us fully support a hypothesis or fully reject a hypothesis. What they do is describe. Another way to think about this is that they're necessary conditions for describing the sample of a population, but they're insufficient for generalizing about that sample or about that population in meaningful ways. Okay, so let's jump in and sort of try to understand what it means for taking a descriptive statistic approach for any kind of data that we might collect through a quantitative paradigm. Okay, so let's think of first central tendency and then measures of spread as being our two branches of descriptive statistics. So the central tendency is the position or the frequency of distribution and where data most often clump together or most often can be observed within that distribution. Now, that kind of sounds like just a fancy way of talking about things like averages. So we remember from grade school or whatever our math background is in terms of creating means or averages, things like medians or midpoints or modes or how often one observation type appears. So a central tendency measurement is going to give us just that, like how frequent do we actually observe one set of observations versus another. Right? And when we plot or when we distribute our data in a maybe two-dimensional plane, we have on the x-axis something like the independent variable, and on the y-axis, remember, our dependent variable. When we plot our data along those variables, right, what we oftentimes come up with is what looks like a symmetrical or a normal distribution. And in the normal distribution, let's think about kind of conceptually what we have here. We have all of our data plotted. And so in looking at the most frequent observations, they should be somewhat together, right? We assume that there's an average to a sample or a population. And as we deviate from that average, we find fewer and fewer examples. That is, in the tails are where there's aberrations or deviance from a central tendency. Now, we might have distributions that look like a positive skew or a negative skew, and these would simply have, say, the ability for our data to be have means or averages which are kind of left of center or right of center. But the important thing to observe here about central tendency, that is when we plot our data along a couple of dimensions, is that we have quite often what's called a normal distribution. And almost all observational data follows this normal distribution. It's one of the fabulous, interesting things about collecting and plotting our data. Now, if our data looks non-normal, that is, it has one of these skews, it maybe looks like what we call bimodal or right skewed or left skewed, then what we probably have is some problem with the sample that we're trying to generalize about a population. That is, we have something like too few observations. We don't have enough so that the data, if it were truly representative of a population, when plotted, would look normal. And so when we don't have enough observations, or when we have two distinct samples, what we might come up with is something that maybe looks bimodal. That is, we have almost two naturally occurring or two normal distributions side by side. And what this would tell us is that we probably have a way in which we could stratify our sample. That is, we could say, this is actually one sample and this is actually another sample, and they both look normal. Okay, so the same thing with right skew is if we have, say, a bunch of data points which clump together around an average here, and we have a bunch of points out on the tail here, then probably what this represents is these points out here aren't really part of the sample or the thing that we're trying to measure about our population. But to try and sum up real quick, a central tendency is telling us about frequency distributions, and when our data looks normal, we should see something like a pretty symmetrical distribution of all of our points when plotted. Now, the other descriptive statistic type that we can use is called a measure of spread. And this is going to tell us how different our data are from one another. And we do this through something that we measure called standard deviation. And this will, I think, make a certain amount of intuitive sense. So let's look at the measure of spread or standard deviation about in two different distributions, both of which are normal. So it's important to note that standard deviation is something that we can only calculate when we have a normal distribution. But standard deviations tell us whether any one observation is surprising or maybe unexpected or expected. And that is, when we have a low standard deviation, our data are all clumped together. That is, they're not deviating much from one another because they're all around the average, right? So if we look on the distribution in the right, this has a low standard deviation. And what we'd see is that all of our data points, right, are clumping around this one central median tendency. Okay, mean, median, and mode tendency. All right, so now a high standard deviation would mean that our data are really spread out. That is, our data are quite different from each other, even though they're normally distributed. So we can see this in our distribution on the left. That is, we have a median, and a mode, which sits here, but we have less, sort of a more distributed data set in that it's spreading out in a more kind of even or smoother fashion. Okay, so the way that I like to think about standard deviations, I'll just kind of like break it down from my mind, is that if we have a mean and we have a standard deviation from that, one standard deviation is going to be kind of normal, 2 standard deviations is going to be really rare, and 3 standard deviations is going to be a complete outlier. Okay, so the other way that you might be able to think about this is, take, for example, something like what our data might represent would be something like the average height of American women. Okay, so the average American female has an average height of 5'6". And so each standard deviation in the distribution of our data would represent 2 inches. Okay? And so 68% of our total population would be one standard deviation one way or the other. In other words, 68% of the population of females living in America are either 5'4" or 5'8"? That's probably true, right? If we just think intuitively about people that we observe in the broad world, 70% of them will be between the heights of 5'4" and 5'8". So that would make a certain amount of sense to us, right? And so our standard deviation then is 2 inches. That is one deviation, which is maybe a little abnormal from the general population, is going to represent 2 inches. Okay, so if we move out then another standard deviation on both sides, what we have are 2 more inches added to the distribution of our population. So now we have 5'2" to 5'10", and that would represent 95% of females in America. Probably also true, right? We don't see many people that are below 5'2", we don't see many people that are above 5'2". Okay, if we go out another 2 standard deviations, we go out to say 5 feet, and we go out to say 6 feet. Now, 6 feet would be very tall, 5 feet would be very short, right? So we would think that 99.7% of our population would fall within that distribution. It's important to note, these figures aren't actually accurate, right? I'm just using this as sort of a hypothetical. But the point being is that when we think about deviations, we're thinking about deviating from a norm. And when we come up with a standard for how much one thing deviates, it tells us how odd or how unexpected our data are. So when we have something that equals 2 standard deviations away, it tells us that it's probably 95 percentile. That is, it's in 95% of what the general population is. If it's really rare, that is, it exists way out on the edges, it's maybe at 2.39%, right? Only 2.39% of the population is in that particular group. That means it's pretty rare. That means we're seeing something that's maybe unexpected that we wouldn't see every day, like maybe a 6'5" person, right? We would probably say, wow, that person's really tall. I bet they play in the NBA or WNBA. Okay, so you're likely saying, that's neat, but what is the standard deviation? How do we actually calculate it? That is, how do we make sense of what might be numerical data, fitting that into a distribution, and then fitting that into, say, a standard deviation? All right, so I'm going to show you an equation next, and then I'm going to walk through what it looks like to actually calculate that standard deviation with a really simple example. Okay, so this is our equation for our standard deviation, and these are the steps to manually calculate how it is we determine what one standard deviation is. I'm going to step through each of these points using an example data set, and I'll put that data set on our course page so you can follow along if you want to. But here is going to be the kind of general makeup of our data set. We have a set of shelters, and we have a set of dogs and a set of cats, which are up for adoption at each of those shelters. Now we have 14 observations, that is, we have 14 shelters at which we might find either dogs or cats, or both. Okay, so at each shelter then we have something like 5 dogs and 2 cats. Now, in order to calculate the mean of our set of data, what we're going to do is simply add up all of the observations that we have for any one particular variable, such as a dog or a cat, and then divide by the total number of observations that we have. Okay, so in our data set, we do this simply by looking at the mean, which happens to be 6.7 for dogs. Okay, so at any one shelter, right, we would expect to find something like 6.7 or 6 to 7 dogs. All right, this makes a certain amount of sense. So now we're going to subtract the mean from each point of our data. That is, for each observation, we'll subtract the mean that we just calculated. Now, this is going to give us likely a negative number if we don't meet that mean. That is, not all of our observations are going to be 6.7 or above. Okay, so as you see in this column here, I've gone ahead and done that. I've subtracted the mean from the observation. And what we get are these set of mostly negative numbers here. But then what our standard deviation tells us to do is we have our observation minus our mean, and we're going to square it. That is, we're going to square each of our data points. So now back into our trusty data sheet, we're going to square that, and we have the answer here. So we've gone from 5 observations, we've minused from our mean, and now we've squared that number. Okay, so now we're at this stage where we're going to start adding up all of the numbers that we've just squared. That is, we add the values from each of the squared steps in step 3. Okay, so now we're going to add all these up, and what we come up with is a sum, something like 86.357. All right, so this is in our little handy equation. In our handy little equation here, we've done all of the top, that is all of the numerator of this equation. All right, so now in the denominator, we have something like n minus 1. All right, so n minus 1, the n here is going to stand for the total number of observations that we have. That is, in our total observations, we have 14. So we're going to take 14 minus 1, and we'll come up with 13. All right, so now we have 13, which is our number here. So just to kind of recap where we're at, we created for each of our observations this number that we then squared, and then we added all of those up. In our column here, that is this number, which is our numerator. This is our denominator. Now we're going to divide 86.357 by 13. And we're going to come up with something like 6.64. And then we're going to take, because remember our equation always under a square root sign, the square root of that. And what we come up with is 2.57. And that is our standard deviation. That tells us from the clump or the mean how much is a standard deviation at any one shelter. That is, if our average, remember, our average mean, that is 6.7, are how many dogs we expect to find at any one shelter, then a standard deviation is 2.57. So 2.57 deviating from that is going to give us 68% of our sample. 2 standard deviations from that, so 5 dogs or 5 cats, is going to deviate, is going to give us 95% of our population, right? That is, if we have a total number of 6.7 dogs that we expect to find at any one shelter, then we could subtract 2.5 or add 2.5, and that would give us 68%. Subtracting or going out another standard deviation would give us 95%. Okay, so you're probably saying that looks like a ton of work, and it is. Thankfully for us, applications like Google Sheets or Excel have handy little equations that we can write. And one of the handy little equations that you can see up here is just an equal sign plus standard deviation, and then we simply select all of our observations, and that will give us the number 3.47. You can see that I've also done this, which gives us the exact same answer that we came up with in doing all of the steps for our dogs. So our dogs 2.57, the square root 2.57 that we came up with earlier. So jumping back in, how we really calculate a standard deviation is that we usually use some sort of formula which is already built for us, just like we do for creating averages, just like we do for creating sums or maxes, right? So in Google Sheets, you can find this by going to Insert, Function, and looking for standard deviation. If you know how to do standard deviations in Excel, you're simply looking at the formula builder and selecting. Okay, so that's how we typically think of descriptive statistics, right? We have central tendency and we have measures of spread. Now, when we're going to report those, oftentimes measures of spread we just do in some sort of statistical commentary. That is, we're offering a discussion of the results using our narrative. Now, when we display something like central tendency, we may use, just like we were looking at before, say a distribution of our data. We may look at tabulated descriptions, which may be tables. We may look at charts or other ways in which we might display our data. But when we have a normal distribution, oftentimes what we're looking to do is describe that through a description like a standard deviation, which will tell us how different or how similar our data really are. Okay, so let's move on to then inferential statistics. Okay, so taking a step back, one of the things that we said about descriptive statistics is that they're oftentimes suggestive of what a population's characteristics are. That is, we're describing things like the mean, the mode, and these are properties, or sometimes called parameters, of what might be generally a population. Now, we said that this wasn't the sufficient data that the sufficient reasoning that we needed to, say, make declarative statements about that population, but they give us a good sense of. The parameters tell us about that population. So for example, 100 exam scores for all of the students in a class like LIS570 may be a population, and a parameter may be the mean score, or 83% of the correct responses in that exam. So inferential statistics are going to be more focused on the specifics of a sample that we've constructed. And when we create a sample of, say, any general population that we're thinking about sampling strategically around, what inferential statistics are going to allow us to do is try to predict, or in some sense, suggest the ways in which that sample is representative of or is not representative of a population. This happens generally in two ways. Now remember, those parameters that we talked about are things like mean and mode. We can estimate those parameters, that is, we can guess and predict what those parameters might look like, or we can test hypotheses. Okay, so when we're estimating parameters, I think this can get a little bit confusing, but essentially what we're trying to do with inferential statistics is, just like descriptive statistics, it sounds just like it is. We're trying to infer through statistical techniques. So think of estimating a parameter as being about how a descriptive technique can be used in an inferential way. Oftentimes what this means is that we're going to take a statistic that's descriptive about our sample data, say our sample mean, and use that in order to express or to say something about the reliability of how well that sample generates to a population. That is, if we have a mean of our sample and it's representative, it should be similarly a mean of our population. Okay, so now think about the example that I used before when I was describing what we might call a parameter. So how well might, for example, 100 students taking a test in LIS570, that is graduate students in the MLIS program at the University of Washington, generate or generalize to, say, the population of the iSchool. That is, students that self-select into my data curation course, how well do they represent everyone that we might expect to find in the undergraduate, the MSIM, the MLIS, and the PhD programs at the iSchool? Probably not very well, right? It's not that one group is smarter or not as smart as the other. It's probably just that that's a very select, very specific group of people that may not be the same as any of the undergraduates or any of the PhD students. Now think about how well that might generalize to the University of Washington as a whole. That is, all the graduate programs, all of the undergraduate programs, all of the professional degrees. Now that's going to be a much more general population, right? We'd expect that there's a lot more skewing or a lot more deviation and spread to the data there. So the point then of using estimates of parameters for the sake of inferring about a population is that what we're trying to do are make suggestions. We're trying to have reliability about how well our sample, say, generalizes to our population. And what we might end up deciding is that we really need a larger sample in order to say something meaningful about our population or to be suggestive about our population. Now, we have a really great use case at our hands here of polling. So polling data over the last few elections have been notoriously bad. And one of the things that pollsters have done have gone back to estimating parameters to think about how they might infer about a population. That is, looking for representative counties, looking for representative voters, and then actually giving weight to voters that they think are either underrepresented in their sample or are overrepresented in their sample. And that way they decrease, say, the importance of those particular people. But one of the things that all polling is trying to do is it's trying to infer about a population from a sample in ways that are going to use descriptive statistics in this kind of logical jumping off point. So how we actually do this in terms of inferential statistics is through something that's called a z-score. So why it's called a z-score is not really all that important. But essentially what we're going to do is we're going to compare a sample to a population given our ability to ensure that we have what we're calculating is a normal distribution. That is, we're sure that what we've collected is kind of a normal sample of data. One way to think about a z-score is it's telling us how many standard deviations from the mean is any one given data point that we have. Even more abstractly, because we're inferring from a sample to a population, what we're essentially saying is how many standard deviations is any one observation in a sample above or below the mean or the average of what we would assume to be a true population. That is, we're going to try to say in some amount of certainty, given any one observation we have, how does it compare to what we would expect the population to actually be? And now a z-score can range from +3 to -3. And what those +3s to -3s actually represent are standard deviations. And think about why this might be the case, right? 3 standard deviations away from the mean would tell us something was 99.7% of the population. That is, it's really, really rare if it's out there past 3. Okay, so in jumping in and thinking about z-scores, that is how we infer about any one data point as being in our sample and how well that represents the population. Let's use this simple example of SAT scores from high school students. Okay, so let's take the mean or the average score of an SAT test being 950. And let's say the standard deviation, that is one standard deviation, is 220 points. Now, noting an SAT is worth a total of 1,600 points. So that means on average, we would expect that 950 is the median or is the mean score, and plus 220 or minus 220 would give us about 68% of the sample. And then plus 440 or minus 440 would give us 95% of the sample. So let's say, for example, we have an observation that is one data point that is student A, and that student A has a score of 1150. And what we want to know is how far above or below the mean with respect to the population that this individual member of our sample represents. So the formula that we use to calculate a z-score is x, and x is going to represent the student's score minus the mean or the average, and we're going to divide all of that by our standard deviation. So the formula that we're essentially using is 1150, which is the student score, minus 950, which is the mean of all scores, divided by 220. And that's going to give us a z-score of 0.91. Or in other words, what essentially the z-score is telling us is that student A is 0.91 standard deviations above the mean population. And if we go back here, we would think that 0.91 standard deviations would put our student somewhere around here on our distribution, meaning they're above average, but they're not, say, wildly scoring off the charts. And if we think about an 1150 out of a 1,600 point test, that's probably about right. They're about higher than 68% of the people that have taken that. So another way that we might think about the reporting of z-scores and how we should interpret them is, I think, made a little bit clearer by this example. So let's say we're reading a medical journal and it states that a patient is enrolled in a study and that patient weighs 240 pounds. Now, for their age and height, it's reported that the z-score puts them at minus 2.0. This would tell us something pretty important, pretty significant here. We would know that the person in a population is 2 standard deviations away from the mean given that weight age, and height. That would mean that of the entire population of people that have been weighed and measured, right, 97.5 percentile would mean that only 2.5% of the people are, say, smaller, shorter, younger. So this would be a pretty significant way in which a kind of savvy researcher may tell you something about the rarity of the person that they're observing, or something about, say, the importance of the person that they're observing and a particular observation in their data set. This is the way that we might use, say, inferential statistics, which are really just descriptive statistics about samples in populations. That is, we're going to try to infer something about how important one person is or one observation is versus any other. So I think it's worth kind of revisiting or stepping back at the end of this lecture of thinking about the different ways we've tried to imagine interpreting and describing samples to fit this into the way that we make sense of the world through deduction. Or we're going to start with a theory of something that we believe about the world, and we're going to state some hypotheses about that. Then we're going to set up a set of observations, and those observations may give us something really mundane. It may give us things like dogs and cats at shelters. But one of the things that we can do is we can set up tests, and we can run tests based on our either inferring or our describing something about that, say, sample of data that we have. And then we can come to a rejection or a confirmation of the hypotheses that we're stating. What we're doing essentially, right, is we're moving from very general assumptions about the world to concrete, specific examples in which we can say that there's a truth value, and that truth value is either accepted or rejected. Now, I think this is really exciting because I think it's one of the ways in which we get to say decisively that something is or is not the case, right? I think it's really fun to be able to look at, say, something as simple as dogs and cats in shelters and be able to say something about whether or not it's really weird to be able to see 12 dogs, say, at a shelter versus, say, 2 dogs. It gives us a way to calibrate sort of the world around us and say whether or not the things that we're seeing are surprising to us or the things that we're seeing are not surprising to us. Now, of course, the problem here is that when we start with theories about things like polling or theories about people's beliefs, what we have is essentially self-reported data, and all the messiness that we have from understanding the way that we communicate with each other, the way that we tell truth to one another, the way that we maybe lie and deceive one another, play into the way in which we can reliably test hypotheses and the way that we reliably come up with some knowledge about the world. But I think it's important to, even if you don't sort of get on board with an idea of positivism or post-positivism, understand the ways in which we can use quantitative analysis to ground ourselves in thinking about whether or not something's surprising or whether or not that thing is just sort of mundane and we shouldn't pay much more attention to it.